Now that we have preferences described, we need to add in the second big component of the theory of the consumer so that we can actually get our way to demand. And this second big component is something we call budget constraints. So we're going to arrive at an explanation of the actual choices that the consumer makes. And when I say choices, what I mean is, given prices and income, what quantity of each of the two goods, good X and Y, or apples and bananas or whatever, what quantities of the goods does the individual choose when facing particular prices and income? So we get to an explanation of choice by combining preferences that we've already talked about with the constraints that we'll talk about now. This is really just the distinction between what we want, preferences, and what we can afford, the constraints. So literally, the budget constraint shows the various combinations of goods that we can afford if we spend all of our available money. So let's jump in. Let's say there are two goods, food, F, and clothing, C. F literally is the number of units of food the individual purchases. C is the number of units of clothing. P sub F is the price of food per unit. P sub C is the price of clothing per unit. I is equal to income. So the budget constraint is this. It says that I can only spend what I have. Another way to say it, though, if I spend all of my income on food and clothing, then that's the budget constraint. So PF is the price per unit of food, times F, that's the number of units of food, plus PC, price per unit of clothing, times C, the number of units of clothing, equals I. So we're going to treat I, income, and the prices of the two goods as given. The individual just faces those, has no control over them. They're outside of his or her control, and we use the word exogenous. The things the individual will be choosing will be the level of F and the level of C. That is the number of units of food and clothing to purchase. Now, it's often handy to put this budget constraint into a slope-intercept form. And so if F, the number of units of food, is on the vertical axis, then the slope-intercept form for us, it means just take the budget constraint and solve it for F. So if we have PF times F equals I minus PC times C, which is just a quick rewriting of that, taking it one step farther, dividing both sides by PF, we get F equals I over PF minus PC over PF times C. And now, I over PF is the intercept on the vertical or F axis, and minus PC over PF is the slope of the budget constraint. So here it is illustrated, the particular example. So if we start just by writing it in this slope-intercept form, F equals I over PF minus PC over PF times C. So for example, if the amount of money available to spend is 20, and food costs 4 per unit, clothing costs 5 per unit, then, well, we can plug in or we can talk about it. Let's do both. So first of all, how many units of F can the individual purchase if he or she spends all their income on that? Well, they have $20 available to spend, and the price of food is 4 per unit. So if they spent all of their money on food, they could get 20 divided by 4, or 5 units. And here indeed is 5. It's also the intercept on the F axis. The slope is minus 5 over 4, so this is minus 5/4 times C. Now what about the slope on the C axis? Well, the individual has 20 to spend. Units of clothing are 5 each. They spent all of their money on clothing. They could get 20 divided by 5 equals 4 units. So this dot here is something that they could purchase. This dot here is something that they could purchase. This dot here means buying 5 units of food and no units of clothing. This dot here means buying 4 units of clothing and no units of food. The straight line connecting them is the green line, and that is in fact the budget constraint. And the slope is minus 5/4. One other point to note, the individual could technically afford points inside of here, but they would never choose that since they like both food and clothing. Just bringing a little bit of an idea about preferences here, the answer is to the question, what would they actually choose, is going to be on the green line. So we'll focus on the budget constraint, not on the opportunity set inside. Let's talk now about what happens to the budget constraint if income changes. So once again, we have the budget constraint written out kind of generally like this. Putting it in slope-intercept form, it looks like this. Suppose we have some level of income I prime that's bigger than the level of income I. How does changing from I to I prime change this expression for the budget constraint? Well, the only thing that changes is this term right here. The slope doesn't change, but the intercept changes. So going back to this picture, here's the budget constraint, the one connecting this dot and this dot, associated with the level of income I. The level of income I prime, which is bigger than I, has a budget constraint that's shifted out parallel. So it has a higher intercept here, and it hits the c-axis out farther, but the slope is the same. So changing I changes the intercepts on the f and c axes, but it does not change the slope. Saying it yet one more way, changing income gives rise to a parallel shift in the budget constraint. Let's contrast that with changing a price. So let's think about changing the price of good F, what's on the vertical axis here. Go back again to the expression for the budget constraint, and we can see now that, well, both the intercept, I over PF, and the slope, minus PC over PF, would be changed by changing the price of food. So if we think about a PF that's lower, PF prime, that's lower than the initial PF, well, how do we think this one through? So first of all, here's the original intercept on the f-axis, I divided by PF. If I spend all my income, I, on food, so divide I by the old price of food, this is how much I could buy. And here's the intercept on the c-axis. If I spend all my money on clothing, divided by the price of clothing. Now let's think about a new price of food that's lower. It turns out because the price of food is lower, if I spend all my money on food, I divided by P prime F is now bigger. So this is higher up this axis. But the price of clothing didn't change. So this intercept stays the same, even on the new budget constraint. So the way we reconcile this is that the slope has changed. The new slope is minus PC over PF prime, and that's a steeper slope than before. The old slope was minus PC over PF. So summing up, if we decrease the price of F, it raises the F-intercept, steepens the slope, and leaves the C-intercept over here unchanged. Let's talk about a few wrinkles with budget constraints. I think these are interesting wrinkles, so this should be fun. So far, our budget constraints have been continuous, as if the consumer can purchase any fractional amount of each good. They've also been straight line budget constraints, which is what happens if the price of the goods is the same regardless of how many units the consumer buys. Those are pretty much the traditional ways of doing it, but and we'll usually stick with continuous budget constraints in the class. But let's just talk about a slightly more complicated example. Since these kinds of examples arise a lot in the real world, it's nice to think about how they look in this framework. So here, let's look at a price schedule for donuts, which I've misspelled in keeping with common usage. Here's the pricing scheme. 50 cents per unit, but then $2 for 6. So if you buy half a dozen, it costs $2. If you buy a dozen, it costs $3. So basically there's a discount for buying a half a dozen and an even bigger discount for buying an entire dozen. Now to think this one through, let's suppose the income the individual has available to spend is $5, and let's define a composite other good besides donuts such that the price of the other good is $1. And then we can think about what the various consumption possibilities are. So in this table, what we can do is put the basically points along the budget constraint that the individual could conceivably choose among. So the individual could buy 0 donuts, and then they would have $5 with which they could buy 5 units of AOG. Or the individual could buy 1 donut, which would cost 50 cents, leaving this should be a 4, not a 5, $4.50 for AOG, and they could buy 4.5 units. Or they could buy 2 donuts, leaving $4 to buy 4 units of AOG. Or 3 donuts, 3.5, and so forth. Let's just jump down to 5. They could buy 5 donuts, which would cost $2.50, leaving them with 2.5 left over to buy 2.5 units of AOG. Then things get a little interesting. What if they bought 6 donuts? If they bought 6 donuts, it would actually only cost them $2, which means they'd have 3 left over to buy 3 units of AOG. And then the process begins anew with 50 cents per additional donut until they get to the 12th donut. Let's contrast 11 with 12. So 11 donuts would cost the price of a half dozen. So 6 donuts costs $2, plus 5 more donuts is 2.5 more, so that's $4.50. So at 11 donuts, they're down to only having 50 cents left, with which they can buy 1/2 unit of AOG. If they buy 12 donuts only costs $3, which leaves them with $2 left over. This is kind of interesting. Here's the illustration that shows how interesting it is. So you see that as they get up from 0 to 5 units of donuts, we're looking at dots that are along a straight line. The 6th donut, though, is not on that line. The 6th donut jumps us up to 3 units of AOG and 6 donuts. And then we're on a line again with a slope that decreases by 50 cents. Or I should say that this budget constraint goes down 50 cents for each 1 donut. We go out to the right. And then at the 12th donut, it jumps up again. Now we can ask the question, just using a little bit of knowledge that we have about preferences, even just the idea that more is better. Are there any numbers of donuts that make little sense to buy? And yes, there are some numbers of donuts that make little sense. For example, you could have 7 donuts and 2.5 units of AOG. So it would never make sense to buy 5 donuts because you could have the same amount of AOG and more donuts. So that doesn't make any sense. How about 4? Does it ever make sense to buy 4 donuts? Well, not really, because you could have the same amount of AOG but more donuts. So these two don't make much sense. Similarly, these don't make much sense either, because this one here gives more donuts or AOG or both. So this is an interesting budget constraint. Might help explain overeating too, but that's beside the point. Let's talk about one other example from real life that's sort of familiar. Let's think about a movie theater soft drink. Now we often see these pricing schemes inside the movie theater. It's $4 for a so-called medium, that's 32 ounces, and then $4.50 for a so-called large, which is 64 ounces. Now let's suppose an individual has $6 to spend and the price of AOG is $1. AOG is the other stuff besides the soda that one can purchase. So what are the choices? Well, one could have no soda and have $6 and therefore 6 units of AOG, or one could have 32 ounces of soda, in which case one would have spent $4, which leaves $2 left to buy AOG, or one could buy 64 ounces of soda for $4.50, which leaves the individual with $1.50, with which he or she could buy 1.5 units of AOG. Just as an aside, it's kind of interesting to calculate the price per ounce. The first 32 ounces, $4 divided by 32 ounces is 12.5 cents per ounce. The next 32 ounces cost an additional 50 cents, and you get 32 more ounces. So the additional ounces in the 64-ounce soda are only 3 cents a piece, a little over 3 cents a piece, as opposed to the 12 cents a piece for the first 32. What does this budget constraint look like? Well, there are these 3 points that are options. One could have 6 units of AOG and no soda, 32 units of soda, or ounces of soda and 2 units of AOG, or 64 ounces of soda and 1.5 units of AOG. And what's interesting about this budget constraint is that, well, it's got a kink. It's not a straight line. Let's talk a little bit about the rationale for this shape. And, just to make this reasonable and sensible, let's suppose that the marginal cost of soda, this is a notion we really haven't introduced yet, but let's just say that it's pretty cheap to make additional units of soda. Let's say it's like less than 50 cents for an additional 32 ounces. That's surely true. Sugar water is not expensive to make. So why might this budget constraint with this shape make some sense? Well, soda, like all other goods, probably has declining marginal utility. So that means an individual is willing to give up a lot of AOG to get the first few ounces, but probably willing to give up less to get subsequent ounces. Think about after you have 32 ounces, are the next 32 worth very much to you? Probably not. So a low price on the last 32 ounces may induce some people to spend an additional 50 cents. And as long as it costs less than 50 cents to make that additional 32 ounces, that could be good for profits. Now I realize I'm getting ahead of myself here, but I do want to link kinds of prices that we see in reality with ideas we have about preferences. And so I thought it'd be good to mention this now. All right, though. What are the takeaways from our unit on budget constraints? It's the following. First, what is a budget constraint? It's the combination of bundles that we can afford if we spend all of our I. That's I, or income. In the linear case, and that's the one we usually work with, so the straight line budget constraint, the intercepts on the respective axes are I over P of X, that is how many units of X I could buy if I spent all my money on X, and I over P of Y, that's how many units of Y I could buy if I spent all of my income on Y. And finally, the slope is minus Px over Py, where Y is what's on the vertical axis and X is what's on the horizontal axis. Nonlinear budget constraints arise when prices vary with quantities. And it's just interesting to note that quantity discounts relate to the declining marginal utility that we talked about earlier.